Okay, now this just to show you what happens under what can happen under river regulations as they're carried out today. The outline here, this green outline and blue outline, is the original form of the Rhine, how it chose to flow in that particular situation. It may have begun to flood because, of course, the forest would have been cut down, although Germany hasn't cut down nearly as much forest as other people have. And maybe it was some way it became inconvenient, or perhaps it was not navigable, and they wanted to use it as a waterway for transport. At any rate, this was installed instead, which is a canal of constant width and constant profile. And suddenly what had been a live thing became constrained in this terrible straitjacket, which didn't allow it to move, and the energies gradually die in it. And so this river has constantly to be dredged. It's not a river anymore, it's a sewer, finally, because instead of the sparkling water that the Rhine used to have, you know, the Rhinegold was what people spoke of, and that was the Rhinegold was because rocks rubbed together of a certain composition on the bottom due to the coldness of the water and the natural flow, producing a glow which is known as triboluminescence, a goldish glow. So people used to see at night glowing along the bottom of the Rhine, and that was the Rhinegold. Well, there's no way you can see that today because it's a grey-green, muddy, slimy, inert brew, and that has all really been caused by the shoving it into a canal of constant width. I think one last thing needs to be said about water, and this is only very, very brief, and that is that probably the best containers for putting water in, if you want to store it, are either egg or amphora shapes, because the egg, again, is a form specifically chosen by nature for the maintenance or continence of life. She didn't choose cubes, didn't choose spheres, didn't choose any rectangular shapes. And water contained in this terracotta vessel would maintain its vitality for a very long time. Firstly, it's cut out from light, so that no light gets to water. The light is the sun and heat are the great dangers for water. And if the porosity of the material is correct, then for each 600th part of the contents that evaporates, the contents will be cooled by 1 degree centigrade, so that if this started out at 20 degrees centigrade, it very quickly would come down to a very cool temperature. And not only that, the water inside it would, because of cooling on the outside, it would descend in a spiral on the outside, moving the central water up, and so there would be continuous circulation. And in such a shape as this, there are no dead corners, no stagnant corners, which there are in cylindrical containers and so on, where there's no movement. And of course, once there's stagnation, then bacteria and all other sorts of things can develop. Now, of course, apart from water, which is fundamental to all life, without the forest, there's also no life for us, because the forest controls the climate. It controls the distribution of water vapor in the air. It also enhances fertility because it keeps the groundwater table up. There's many things that the forest does. It tempers everything for us. So without forests, in fact, we have no future, which is why I put this up. And this is one of the things that I think has to be pointed out, that while it is very important that all sorts of devices should be designed and produced to create free energy or as cheap energy and as environmentally sustainable energy as possible, the bottom line is there has to be some greenery out there, because if there's no greenery out there, there's no oxygen and there's no life and there's no rainfall, because everywhere we've seen that the forest has disappeared, then the drought has moved in. So it is a fundamental importance for us that we should plant more trees as fast as possible, and in fact one almost might say that all the unemployed people who are unemployed at the moment, of which there are vast numbers in most of the so-called civilized countries, they could quite easily put their hand to reforestation if it was done organized properly. But what we really need to find out too is what value do trees have for us? This is an evaluation of a 100-year-old tree by Waltera Schauberger and what it actually has done during its 100 years of life. And during this period, it has photochemically converted 9,100 kilograms of carbon dioxide and 3,000 liters of water. And it stored about 23 million kilogram calories which are equivalent to 3,500 kilograms of pit coal. And it is made available for the respiration of man and beast 6,600 kilograms of oxygen, so that in its 100 years life, this tree has produced 6.6 tons of oxygen. In addition, it has evaporated into the atmosphere at least 2,500 tons of water, and has supplied a member of the Consumer Society with oxygen for 20 years. So in view of this marvelous production of trees, which it does with giving, there are no unions involved in trees. They give all the time, and their giving is unconditional. And this is something maybe we should also think about ourselves, because in order for evolution to proceed, the giving must be in greater measure than the taking. Because if everything is taking, then finally the pot is empty. It can only succeed if the pot is continually being refilled or being filled up more and more. Basically, there are 7 types of tree, and they are determined according to whether they're light demanding or they're shade demanding, whether they're hardwoods or whether they're softwoods, whether they're coniferous, deciduous, or they are a rainforest tree. Now, as far as light demanding timbers are concerned, they mostly have a thick bark, whereas shade demanding timbers have a thin bark. Hardwoods can be either thick or thin bark, as can be softwoods. Now, a tree, again coming back to the origins of energy, the energetic basis for all things, a tree is a mirror of the quality of light that falls upon it, a quality of the energy in its environment. So that in a situation where the tree is exposed to hard light, which is blue light or ultraviolet light, the wood is soft. And where the light is soft, which is red light or infrared light, where those frequencies of light predominate, then the wood is hard. So the tree is a mirror of the quality of light. If the light is hard, the wood is soft. If the light is soft, the wood is hard. And of course, there are all sorts of graduations in between. And even the shape of the tree is affected to a certain extent by its location in altitude, because the lower the altitude, the greater the preponderance of infrared and red light, and the higher the altitude, the greater the preponderance of blue and ultraviolet. Again, there's this levitational energy spiral which moves upwards against the forces of gravity, which is why the tree also grows upwards, why we stand upwards, why everything knows which way up it's supposed to be. And in an isolated environment, then the tree near the equator tends to spread laterally, because this movement of energy is not very strong going upwards. As we get to higher latitudes or higher altitudes, then the energy, upward energy, increases, and it's reflected partly in the form of the tree. So that high altitude trees tend to be rather more pointed than very low altitude, low latitude trees. What is important, particularly important in reforestation and in trees generally, is to understand what is a shade-demanding tree and what is a light-demanding tree, because this doesn't seem to have been taken into account in forestry, in modern forestry. This is a photograph taken on my property in Australia shortly after I cleared some land around these 2 trees. This area under here was covered with a very dense undergrowth, lantana it's called, which goes wild in Australia. And so these 2 trees, which are these 2 trees here, grew up with the bottom part of their trunks protected from light. About 4 weeks or 2 weeks or so, somewhere in that sort of period, I noticed that one of the trees was growing some branches on the lower part of its trunk, and the other one was not. And I'd been looking at this because I had also been studying this been involved with Viktor Schauberger's concepts for quite some time. But this tree is a shade-demanding tree because it's put out branches to protect the trunk from sunlight. The other tree is a light-demanding tree. It has a much coarser bark, and it didn't put any branches on. Now, why did the tree put branches on? What was the necessity for a shade-demanding tree to add branches to itself? Well, what is very critical for a tree and for the health of the tree is the movement of sap and the tree's internal temperatures. So that when the sun impinges on thin bark, of course there's no insulation, or virtually no insulation, and the temperatures within the tree start to rise, and this causes a dislocation in the natural movement of the sap. So in order to protect itself, the tree immediately puts branches on the outside against the sun. So while we tend to think that trees and shrubs put out their branches to catch the light, they do so in fact to protect themselves, their center part of the tree, from light, because otherwise all their metabolism gets upset. Now this is very, very serious when it comes to large-scale reforestation and large-scale planting. Just to show you how this this effect also happens, here this is again a profusion of small branches. This tree was suffered from a forest fire, and so all the way up every branch as far as possible there were little shoots brought out, because in the fire all the outside skin of the tree had been turned black, which absorbed all radiation and all heat. So if the tree was to survive at all, it was absolutely imperative that this blackness should be protected by a color which is natural to the tree and would normally reflect the sunlight. Again, by overexposure to light demanders, when they're overexposed to light, they produce some peculiar characteristics. This is a small beech tree growing at the side of a forest, and normally most of the development of a beech tree is up in the crown, but there are myriads of little branches down below which make the wood very knotty. Again, because of the disturbance in the sap flow, this is another light, shade-demanding tree, and you can see that the trunk is actually conical, and that is because due to the heating processes within the trunk, all the nutrients are deposited sooner than they should be, which adds to the girth of the trunk. Whereas that same tree in its natural state would have a virtually cylindrical trunk, and all the development would be at the top. This tree here has been exposed to electromagnetic radiation in the form of radar and microwave activity, which has created a distorted form of the tree. You can see how chaotic it looks. According to the German engineer Dr. Wolfgang Volkert, microwave senders, which are these communication senders, act in the same way as microwave ovens, and any living thing exposed to them gets cooked virtually from the inside out, because he noticed that in Germany, when a new tower was put up, and he made a study of it, on all the slopes of the hills and mountains facing the tower, the trees began to die off, and on the opposing face, on the shadow side as it were, they were still okay. And one of the reasons for this is that one of the wavelengths that they use for microwave transmissions is 21 centimeters, which is the natural harmonic wavelength of hydrogen. And so the hydrogen atom within the water molecule becomes excited and disturbed, and perhaps even removed from the water molecule, which then of course upsets the whole of the sap flow and everything else. But it would also upset anybody else who happened to live there. The trees can't move, they're rooted to the ground, human beings and animals can. But I would imagine that because of this, that anyone living under the path of one of these microwave senders would be more susceptible to disease than someone without. That was a slight digression. I would want to continue with the effect of light and understanding it on trees. Here there's another tree with the branches all on one side. And again, from our conventional point of view, we'd said, oh, well, he's got the branches here because that's where the sun is, and it's putting it out to catch the light. There are no branches on the other side because there's no sun. In effect, that is true. But the proper interpretation, or at least Viktor Schauberger's interpretation, is that the tree put branches out in order to protect itself from the sun. No branches would go on the other side because it didn't have to protect itself from the sun, which is exactly the opposite way of looking at things. Viktor Schauberger often said that if you want to know the truth, of how something should be done, find out what today's technology is doing, and do exactly the opposite, which means really a 180-degree change in our point of view. Here, another tree. This is a tall pine tree. You can see there's a lot of branches all the way up and down the trunk. It must have been left perhaps as a mother tree in order to provide more seed, but when its neighboring trees had been cut down, then it had the necessity to grow all these branches up and down the trunk on the outside in order once more to restore its inner temperature conditions, crucial to it. These again, oh, that's the same one as before. Again, here's another tree. The lower branches have been cut off, and then suddenly you get a profusion of branches growing on it again. Same reasons. And when you compare the girths of naturally grown and artificially grown plantation timber, now this is a fir, a shade-demanding fir, the big one, and as a result of overexposure to light, then all the annual rings have been spaced apart, the wood is spongy, the whole metabolism of the tree has been upset, and so you get huge growth. You get quantity at the expense of quality. There's no quality in this, and most of this wood would be unsuitable for any structural purposes. Whereas these other trees here, also fir, are the same age as far as can be seen, because their annual rings are so close together they're almost indiscernible. So these are the two differences. This is very high quality wood, and this is very low quality wood, and this sort of wood is what is being produced in most of the plantation forests in so-called reforestation projects. Because in all reforestation projects, it should be important, it should be obligatory to plant as many different species as you can instead of a single species. Otherwise you arrive at a monoculture, and once you have a monoculture, you introduce into a natural setting what used to be a cooperative process into a competitive process, because all the trees in the monoculture have to draw their nutrients from the same horizon. They're all the same species of tree, they've got the same root patterns, they take the same amount of moisture, they take the same energy from the sun, they reflect the same light frequencies, and so there's a total wastage of energy at the same time as the tree is also trying to take from its neighbors whatever it needs to survive. How this the effect of heat on the growth of the tree is more apparent in this diagram, where on the shadow side of the trunk, so to speak, then the annual rings tend to be close together, the sap waves are finer, the movement of sap up and down the tree on that side faster, whereas on the other side of the tree, which is exposed to sunlight, then the annual rings become wider, the material between them pithier, and the movement of sap slower, and under normal conditions a lot more branches would grow out from that side, making the timber virtually useless because there would be too many knots in it. And when sap moves up and down the trees, in a healthy tree, and a shade-demanding tree in this instance, in this proper environment, then there are virtually no branches which are produced on the trunk. The trunk is virtually cylindrical, and because there are no branches, there's no impediment to the movement of sap going up the tree. So it can rise to the top of the tree, which could be 150 to 200 feet high. And the sap waves are very small, the sap ducts are very small. And now, how does the sap get up there? Because, of course, under normal suction, you can't raise water up more than about 9.8 meters by suction. And osmosis won't take you that much further either. So how does the sap actually get up there? Now, according to Viktor Schauberger, as the day warms up, or as the climate warms up, the season warms up, there's a general rise in temperature. And all the carbonic acid, which is in the sap, which is in the water, gradually warms, and a certain portion of it then turns into carbon dioxide, which is a gas. And these bubbles of gas then fill and block off the sap ducts, and like corks they rise and they push the sap and the water ahead of them right to the top of the tree. And at night, when it cools slightly, they fall down, and then they draw in all the sugars and starches and the nutrients and the gases which have been formed during photosynthesis during the day. So that's what happens when you have a naturally grown tree with very tightly spaced annual rings. When it is a plantation tree, then the rings are wider apart, there are more branches, but also the sap ducts are commensurately wider apart, but the bubbles of carbon dioxide are not sufficiently, they don't expand to fill these ducts in the same way as they expand to fill these ones. And so the sap is not lifted, the nutrients are not lifted as high as they would be in a healthy tree, and therefore they're deposited at the base, which is why these trees then are more cone-shaped at the bottom. Instead of being straight, then they have this shape, which of course everybody thinks is ideal for a Christmas tree, very picturesque, but actually a Christmas tree like that is a very unhealthy tree. Trees have a function. Not only do they give us oxygen, but they also have a symbiotic interaction with trees, in that they provide for us the color we need most for rest and peace of mind, which is the color green, because trees absorb light by and large in the ultraviolet violet part of the spectrum, and the infrared and the red part of the spectrum, but they do not absorb light in the green part of the spectrum, so that is what is not absorbed is reflected. We, on the other hand, are not very sensitive to ultraviolet or infrared, but we are very sensitive to green. And green is the color that the trees give us, and if there's a lack of greenery, then I think it has quite an effect on the psychology of the people who are living in such an environment. In many modern cities there are very few trees, and I think this must lead to an increased violence, a fundamental rising of the disturbances in the nervous system. And also, of course, then there's a lack of oxygen, which produces anoxia and various other things. Trees can also be likened in Viktor Schauberger's to biomagnets rather than magnets. A magnet we usually view as being a bar magnet, which has a north pole and a south pole, and the magnetic lines of force go from the south to the north, and they spread out across the middle. And that is generally what our view of a magnet is. However, a tree has a completely different form of being a magnet. This is one which is based on a hyperbolic cone. Again, this is actually a bit cone-shaped in form, but if you can see the way the forces arise inside this tree, that there is, this is an experiment I carried out, so I measured exactly where all these filings are moving to, and out of the top they flow, out of the top they flow in towards the sides, and they flow in from the bottom. So in a sense you can get a picture of what I mean, this form, the hyperbolic cone, is again to do with non-Euclidean geometry, which is the geometry of nature. And so you can see that a cone taken in this shape seems to already give the pattern for the growth of a tree, because all the way all the filings on this are disposed gives a very tree-like form. Okay. If we come back to if we were to view these as the annual rings on a tree, water, as I think I mentioned when we were talking more about water, has a dielectric value. It has a very high dielectric value, which means it's able to resist the transfer of charges from one side to the other of it. If in the tree we have the green part is water, which eventually then becomes the annual ring, then on each side we have positive and negative charges. As the surface area of the outside blue cylinder is larger than that of the inside red one, then the density of charge, the intensity of the charge on the inside one is greater than it is on the outside one. And as a tree is made up of a series of concentric rings, then the charge from the outside increases as we move towards the inside. But under certain conditions, the energy of the tree can be severely disturbed because of the distance and the spacing between it. Now, when we're looking at the terms of separated charges of positive and negative, the closer the charges are together, the greater the potential. In that sense, the greater the life force. The further the charges are separated apart, the lower it is. Now here we have a 33-year-old tree, a section through the trunk, and you can see straight off that this was a plantation tree because the annual rings in the middle are very widely spaced apart. That means that when the tree was a young, struggling little tree, a sapling, it was exposed to far too much sunlight. And so its girth widened at the base, and gradually, as its neighboring trees grew up, then it became more and more protected from the sun, and the annual rings got closer and closer together. At 26 years old, someone came and cut down all the trees around the outside of it, and at once, all the annual rings then expanded. Now, the time that this tree was actually healthy, it was in this part of its life. Whereas here it was unhealthy, and in the center it was unhealthy. And in terms of the life force, the potential, so to speak, between here and there, the life force would have been much less because the charges of positive and negative were separated by much greater distances. Here they would have been very close together, and so the two charges would have been closer together and the potential much greater. And so this graph at the bottom here, the blue one, shows you really what the potential levels are, their nominal values, as you move from the outside to the inside. So from here to here there's virtually nothing. Suddenly they peak because they get very close together, it falls off, and then from there to there's nothing again. On the other hand, the actual generation of a charge from the outside to the inside does increase constantly. It's difficult I have to differentiate between potential and charge. Potential is the life force. It's a different energy from the electrical charge, which can be measured from the outside towards the inside. Waltera Schauberger made some probes, and he probed one probe very deeply into the center of the tree and the other one on the outside. And in that way, he was able to make light bulbs light up. I'm not sure whether I haven't mentioned that already, but that is the process. Why does growth occur at the extremities of the tree? Why is there not more growth down the center? Well, if we look at this tree as a system of energy pathways in all the little tubules and sap ducts and so on, when you get to the top of the tree, then these are all very close together, which means that they're minute in size. And in a sense, also, there has been a tremendous increase in the potential in the life energy of the tree at that point, so that what is passing up these very small sap ducts are only the very finest materials, the sort of homeopathic substances, which, because they have been potentiated, create the greatest energies for the tree to grow. Whereas down here at the bottom, this doesn't occur in the same measure. Very important too in our understanding of the interaction of trees is also the root structures, because we can create an enormous amount of harm by pulling out a species of tree which may have a certain root structure which helps the whole balance of the forest. And although these aren't trees, I'm going to put these on one after the other in order. Here you would see a very simple plant, which perhaps was the original plant which grew in this place, maybe a sort of primordial plant. In the process of growing, it made a little bit of shade on the surface. It created coolness below the surface. It trapped a few particles from the wind, and that allowed another plant to develop. But this other plant had roots which came in a different area. They didn't actually compete so much with this one. It had a different root shape, and it was more broad spread, and it again created more cooling. That means that the depth of moisture would increase. More particles were trapped by the wind, which then would allow another plant to come and take root, which had a deeper root system. And that in turn multiplies more complexity, better ground cover, and another plant with a different root system would come in, would grow, and this would give way to the possibility of yet another one to come, and so on. So all these plants gradually, these are all real plants, mind you. These are not just drawings. There's someone actually measured all these, they're actual plants. So by the time you get you know, you get a significant complexity of roots. But if this one, the last one I put on, was the major one, which was the major species, which happened to be very good for making furniture with, so everybody took it out, then when I take it away, suddenly, where's the water going to come from? Because this plant was actually going down and getting the water and bringing nutrients up for the other plants. So it's very important that always there's as many varieties of plants and trees as you can have in a normal forest. These are more or less the same roots that I showed you before, but that is their relative distances. This is 4 meters below the surface, and the other ones are there. These are actual plants, and it shows what and this is only a few, because the book that I have has got about 260 different root systems like this. So when you understand this complexity, this huge Gordian knot which is occurring underneath the ground, then it begins, you understand why it is so important to have all the diversity, because it's the diversity which allows all the plants to take from different areas, to take minerals, and they don't compete with each other as they would in a monoculture situation. Okay, now we're going to dip lightly into the mathematics of all this, which have largely been determined and formulated by Waltera Schauberger. Waltera Schauberger was a physicist and a mathematician, and when his father died, he agreed, or he promised his father, that he would try and develop a system of physics and mathematics which would explain Viktor's theories in a way which was irrefutable, so that it could never again be said that Viktor Schauberger's machines didn't work or that his theories were invalid. And it was this task which Walter set himself upon the death of his father in 1958, at the time when they came back from the United States. Waltera Schauberger's mathematical system is based on the harmonics of the monochord. This is an instrument which was used by the Pythagoreans in order to determine harmonic intervals on a resonating string. And these intervals can only be determined, or can only positioned at whole numbered divisions of the string, so that if you divide an open string 1 into a half, then you get the first octave. Just to the right and the left of this point half position, you will not get a state of resonance. It only comes when you have done it exactly on the point divided by, where you've divided the string by 2. The same occurs when you divide it exactly on the point dividing the string by 3, in which case you get a sort of tripartite waveform which moves between the nodes of where the string is divided. When you divide it by 4, then of course you get the second octave. And so that any string of whatever kind would produce at once a series of overtones, which are the overtone series which rises from above them, and also in the same sense a series of undertones. And Pythagoras and the Pythagoreans made a study of these because it was important to determine the harmonics of things, because they saw the world as being the manifestation of qualities and harmonics or harmonies. And in fact, a student had to study or pluck upon a monochord for maybe a year or 2 years until he could hear 120 harmonics on the string. Now that means the harmonics were going to an extremely high level. This was then important in order to realize how, just before I continue that, actually, just to show you how this links up with the hyperbole we saw before. If I can put that to the side and put this on here, then you will remember. Then you can see that the full length of the string is 1, which is from here to here. The half is there, and the third is there, and the fourth is there. So that in fact this whole hyperbola, it represents the division of a string into an infinite number of integral divisions, i.e. dividing by a whole number. And as it's infinite, so at the top of it, the quality, in the sense of quantity times quality, the quality is infinitely high, as is the vibration at the top. And this gives us some idea of how higher qualities and higher energies and higher vibrations become the controlling force, because if we take, for instance, these vibrations at the bottom, we'll say they're 1, 2, 3 cycles per second, or 2, 3, 4, 6 cycles per second. In order to be able to resonate with more and more, and to be in harmony with more and more things, we have to raise our vibration so that what is the next higher vibration is in tune with all of these. So if we take the next higher vibration, for instance, as being these green ones, then the vibration of 30 cycles per second is directly harmonic with 2, 3, 5, 6, 10, and 15, all of which numbers will divide equally into 30. Or 12 would be 2, 3, 4, and 6, or 10 would be 2, 4, 40 would be 2, 4, 5, 8, and 10, and 20. But again, once again, these, in order to combine them into a harmonic whole, they need to be, again, associated to a higher number even than themselves. So a number 120 would be the number in which to all these various numbers, 1, 6, 10, 12, 15, 20, 13, 40, are all can all divide into equally. So that we come back to what I said earlier on about energy, about the higher energies being the formative energies. And when we look at this vibrating plate, we can see again how vibration creates a particular form. Here is a square plate with sand just sprinkled over it. The vibration is started, and gradually the final form arises. And when that vibration is doubled, or when the next octave happens, then, as is shown in here, which is a different pattern, then the pattern becomes more complex. So here we have the first, what you might call the bass tone. There is the first octave, there is the second octave, and there is the fourth octave. Again, the complexity increases as the vibration rises, but the form still has the same fundamental characteristics. And it seems to me that all physical manifestation is based on states of resonance, and these are very critical and they're very precise. As we saw with those sand plates, a particular frequency produces a particular phenomenon. And therefore, if we want to arrive at phenomena, or if we want to recreate phenomena, then we need to arrive at those frequencies which are conducive to its formation. Unfortunately, the way most large numbers are handled, and here we are dealing with large numbers, is done using scientific notation, where a number is written as, let's say, 2.5 times 10 to the power of 26 or something like that, which means that it's the number 2 and then the number 5 and 25 zeros coming after it. And if you were trying to seek a particular level of resonance, you would need to know exactly what the last digit of all those 26 digits after the decimal place were. And this is what gets lost out. This is what we lose with scientific notation. On the other hand, with computers today, there should be no problem in determining a frequency value up to the 20th and 32nd place of decimals in order to find precisely that frequency which would, from which a particular form could evolve. Interestingly enough, also, that if we're looking at resonance, then this is, wait a minute, I don't want to sit there. These are some figures that I just came to me slowly as I was doing all my research, and it seems that the number 29 or 2.9 or various forms of it seem to have a peculiar coincidence with planetary phenomena. The speed of light is 299.7 kilometers per second. The Earth's natural resonant frequency is 29.97. The mean diameter of the Earth's orbit is 299.1 million kilometers. the Earth's mean orbital velocity is 29.79 kilometers per second. The length of the lunar or synodic month is 29.5 days. Saturn's orbital period is 29.46 years, and so on and so on. So the number 29 seems very strange number, and associated with the Earth. We discussed earlier also the geometries, and this actually puts them more under the limelight, because this section we're actually dealing with the mathematics. Now, this compares the two geometries, the non-Euclidean and the Euclidean. Nicht-Euklidisch is non-Euclidean, Euklidisch is the Euclidean system. Here we have the circle, the straight line, the point, the radius. And here these shapes are these ovals, or these ellipses, are taken as sections through a cylinder, taken through a right-angled cone, which means a cone where the shape is actually a right angle and it's circular this way. Any inclined section through a cone will also produce an ellipse. So all these are the elements of our technical world. So the circle, the straight line, and point are all part of the same element, in fact. The circle has a certain radius. If I reduce the radius to 0, then the curvature is infinite and I have the condition of the point. If I increase the radius to infinity, then I have a position where the curvature is 0 and I have the straight line. So the straight line, the circle, and the point are all aspects of the one element of the circle. But the circle and the straight line and point do not exist anywhere in the physical universe. They are of the mind. They are transcendental. They belong to the realm of measurement between things. They belong to the realm of thought, excuse me, but they do not belong to the physical world, because we cannot describe natural artifacts using those particular elements. The ellipse belongs in these systems because the ellipse is in fact an extended circle. It's like taking the center of the circle and dividing it in two and pulling it out, and then you get an ellipse from it. So they are all closed systems. They are all perfect. They cannot be varied, because a circle is a line of constant curvature, no thickness. A straight line is a straight line. A straight line means there's no variation. There's no movement about it. It's totally perfect. It therefore cannot reflect any system in here, like in nature, change is in here. There has to be constant change and transformation. And so this is represented by non-Euclidean geometry. And this is the geometry of nature. Using this geometry, then we can draw the development from the formula which I showed you before, which had the hyperbola. That was the elevation of this spiral form. The spiral form, we were looking at it on the one from scale. We will have a larger spiral at the moment, but this spiral starts alpha, or alpha infinity, as Waltera Schauberger called it, which is the beginning, and by rotating an almost number of times seeks always to strive to reach the point, omega, moving from the straight line to the point. And this is the curvature of matter, of the descent into matter. And the nature of this particular curve is such that no two parts of it are identical. And so within this also is underwritten not only the discontinuous aspect of evolution, which is the production of individuals, of individual things, but also the continuous movement of evolution into states of higher and higher order. So along this line, this spiral line, every degree, every every part of it, the curvature is different. You cannot take a part out here and put in here. It doesn't fit anymore. And so every individuality, all the myriads of atoms, every single thing that exists in this universe can, in a sense, be represented by a small part of the spiral as its characteristic, because there are no two parts of it alike. As you progress towards the center, of course, the velocity increases, the energetic activity increases, and you get closer and closer to God, so to speak, because originally Walter called just the theocentric system, wherein God lay at the center. And the only way, in fact, to reach him was to jump out of space and time. So the curve, as it were, is space-time continuum. The straight line is out of space and time, and so is the point out of space and time. But they are the two bridgeheads from which life springs into physical existence. Interestingly enough, also, this spiral connects the points of the triangle, the square, the pentagon, the hexagon, the heptagon, the octagon, the nonagon, the decagon, etc., 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 etc. And one of the amazing things about this is you begin to learn how nature can divide things up with equal angles. If I can find the thing. Where is it? No, this is what's getting out of context. Just to show you how this form is also, this hyperbolic spiral appears in nature. This is a meteosat photograph. Here you have the diagram I showed you before, and this is virtually the same energetic wall. This is a low pressure system, and again, it's like the tornado. The energy, the closer you get to the core, the greater the energetic content. Again, the same math can be used to explain galaxies. You can have a galaxy much the same as this, and also as I overlaid that galaxy earlier on in the show. Into this too are all the various this hyperbolic cone again can be used to explain all the different frequencies. From ultraviolet, visible light, infrared, radar, and so on, all as questions of wavelength, of distance from the central axis to the outside edge of the hyperbola. If we move in now on the spiral, we can, to go to a closer view of it. We have made, so to speak, one full revolution from alpha, which is infinite distance away there, and we've gone round completely once. We've turned around through 360 degrees, and we arrive at the value of 1, because we have made one total revolution. And at that point, we can say that the string length, so to speak, is 1. We have completed the period of what you might call pregnancy, because before 1 there is nothing. There is no wholeness before we arrive at the 1. And after that, then we enter the world of the physical world. Before that is still transcendental, and from this point 1 onwards, there has become an individuality. Before an individuality, there is only energy. And with a string length 1, after 1 full revolution, we have moved into a position of a half, into a third, into a quarter, into a fifth and sixth. Exactly the same in reflection of the hyperbola which went up in the other direction. So here we would have the distance 1, there would be 2, so the elevation of this would be a curve which goes up in the opposite, in the other dimension. And into this can also be interpreted musically, because the string length being 1 would have a certain tension, and then as we reduced the length of it, the tension would give rise to all the various notes that we're aware of, and it would be just wherever the string length is, gives you whatever the note is, so to speak. And then you find some interesting relationships that in the major notes on the scale, they are always divided by multiples of 15, 30 degrees, 60 degrees between F and G, and so on. And the other half notes are in multiples of 3 or or 9. So one begins to get certain insights into to the patterns of energy by looking it through the spiral form. This is also another one which interprets in terms of color, that you start with the base tone where you've got the rather darker color. As you move around, then the color becomes a higher frequency, so that it's a lighter color, but still going through the full spectrum, so that it begins to teach you how eventually all colors return to the source from which they came, which was white. And also an idea of the higher vibrations of colors that, for instance, clairvoyants and other sensitives are aware of, which are really merely harmonics of the lower ones. This spiral that we saw before is also the spiral by which you can use to divide any angle into any equal parts, any number of equal parts. Now, if you've looked at a pineapple, you've seen that it has spirals on it, maybe 13 going one way and 34 going the other way, or on a pine cone, there's 5 going one way and there's 8 going the other way. So how does nature make these beautiful divisions? Because 13, to divide 360 degrees by 13 is a bit difficult, or by 24, or by 33. But if you take this hyperbolic spiral and you want to divide an angle, let's say this angle AB, then you take your compass, you make a mark at the top and the bottom where you want to incorporating the angle, and then with that radius you multiply that radius 5 times if you want to divide that angle by 5. And once you've multiplied the radius 5 times, then you have this length here, the green one, which then has the value of 1. And you draw an arc from the center to where it cuts the hyperbolic spiral, and you draw a line to the center. Then you reduce the radius to a half, and you do the same, and then you take it to a third, and the same, and a quarter, and do the same, and finally to a fifth, and you divided that angle into 5. And here again is the hyperbola when you connect all those lines together. So it's a kind of mathematics which seems to be very integrated. If you take a section through the hyperbolic cone, then you can get fish shape. This is the hyperbolic cone, part of it there and part of it here. And taking an angled section through it, the flat plane that you can see would have this form. And there's a bit of the tail of the fish too. If you cut it in another section, slightly flatter, then the egg can be obtained from that. So with this system, it's possible to create any egg precisely and mathematically to determine it. You can design your own egg, so to speak, the one which is most suited to whatever purpose you require. And according to Walter, maybe it was even in the shape of the egg itself that the flight characteristics of the different birds were, because one kind of curvature produced one form, a different curvature on the egg produced a different kind of bird. I don't know if anyone has really made an accurate study of the precise dimensions, but they're all different sizes of egg, and all the birds have different flight characteristics. And so in using this process, I've actually been able to make some eggs. These ones hold about, I think it holds about 5 gallons or something. It was made as a water device. A little bit more how you can make sections through these cones. These are various sections taken through the cone, and from these you get a number of different egg shapes. This one, for instance, would be taken. It's difficult to do this without relation to the cone. I'll try and put that back here. No, I think I'm going to take it out. It depends how pointed the egg is, depends on how steeply you make the cut through the cone. And it doesn't matter where you make the cut on the thing, you can always define it from a mathematical point of view. These are all different egg shapes. And these are the data which correspond to it, so that it does show you that they can be very precisely defined It's a different one. I'm afraid it went slightly wonky at the end. And there's another one which is more leaf-shaped. So all these can be drawn out of Waltera Schauberger's maths, which again is this very simple form of maths based on the equation 1 over n times n equals 1. And I think probably there's just one more point that I would like to make, and to show how this relates to the orbits of the planets. That if you, this is the same sort of section that we had before, where there are various sections taken through the cone. Now these ones correspond to the planets themselves. I did this one deliberately to find them, and so this orbit here is the orbit. Now we say egg-shaped orbits, and actually it's the inside one is egg-shaped. The outside one is the corresponding shape of an ellipse, using the same eccentricity, as it's called. There's one focus and there's the other focus if this were ellipse. If this is an egg, there's only one focus, which is here, and that concerns the inner line. Now, if you were trying to find a planet, in this particular instance, this being Mercury, there's a variation of something like 4.8 million kilometers between here and here. So if you were trying to land a spaceship on Mercury and you were using Euclidean geometry, you could be quite a long way away. And I do believe that when they tried to land one of the landings on the moon wasn't where it was, and they had to use up quite a lot of fuel in order to actually get there. And the thing may have been the result of this discrepancy, that the moon was, they thought was here, but it actually was here because it was following an egg-shaped orbit rather than an elliptical orbit. And these planets then can also, interestingly, they also follow a line, a hyperbola, where you have the orbital velocity times the distance from the sun. And those create a constant, and so you can plot very easily the planets lie on this hyperbola. So the mathematics of Waltera Schauberger and his father's processes, which are always these reciprocal things which end up in the unity, or they show how energy can be created, or the paths that energy wants to move in, are very much integrated. And I think they really need to be brought into focus for a new direction in environmental treatment, a new direction in water resources management, forestry. In fact, a new direction in almost any avenue of human endeavor that you can think of, because we seem to be doing it wrong. If we were doing it right, we wouldn't have the problems we have today. And it seems to me that Viktor Schauberger and Waltera Schauberger have some way, they're not the solution, but the solution at least, which allow us to understand how we can change the environment, how we can restore the climate to a state of balance, how we can do so many things to improve agriculture so that we can have far more people alive on this planet, but fed well, all those things. Some of the information which Viktor Schauberger has to offer can finally be integrated into a different society. Viktor had one thing to say, and I quote him. Firstly, well, two things. First is, if you want to know what the right thing to do is, do exactly the opposite. You must comprehend and copy nature. And then from him, which I think is telling, is they call me, the hope is that they are right. For it matters, it's a little important on this earth. If I am right and science is wrong, then may the Lord God have mercy on mankind. And he wrote that in 1930, after seeing what would inevitably happen if all the various technical processes we set in motion continued unchanged. And that is exactly where we have got today. In 1930, he forecast all the environmental problems we are having today, and he said exactly why. So. society with oxygen for 20 years. So in view of this marvelous production of trees, which it does with giving, there are no unions involved in trees. They give all the time, and their giving is unconditional. And this is something maybe we should also think about ourselves, because in order for evolution to proceed, the giving must be in greater measure than the taking. Because if everything is taking, then finally the pot is empty. It can only succeed if the pot is continually being refilled or being filled up more and more. Basically, there are 7 types of tree, and they are determined according to whether they're light demanding or they're shade demanding, whether they're hardwoods or whether they're softwoods, whether they're coniferous, deciduous, or they are a rainforest tree. Now, as far as light demanding timbers are concerned, they mostly have a thick bark, whereas shade demanding timbers have a thin bark. Hardwoods can be either thick or thin bark, as can be softwoods. Now, a tree, again coming back to the origins of energy, the energetic basis for all things, a tree is a mirror of the quality of light that falls upon it, a quality of the energy in its environment. So that in a situation where the tree is exposed to hard light, which is blue light or ultraviolet light, the wood is soft. And where the light is soft, which is red light or infrared light, where those frequencies of light predominate, then the wood is hard. So the tree is a mirror of the quality of light. If the light is hard, the wood is soft. If the light is soft, the wood is hard. And of course, there are all sorts of graduations in between. And even the shape of the tree is affected to a certain extent by its location in altitude, because the lower the altitude, the greater the preponderance of infrared and red light, and the higher the altitude, the greater the preponderance of blue and ultraviolet. Again, there's this levitational energy spiral which moves upwards against the forces of gravity, which is why the tree also grows upwards, why we stand upwards, why everything knows which way up it's supposed to be. And in an isolated environment, then the tree near the equator tends to spread laterally, because this movement of energy is not very strong going upwards. As we get to higher latitudes or higher altitudes, then the energy, upward energy, increases, and it's reflected partly in the form of the tree. So that high altitude trees tend to be rather more pointed than very low altitude, low latitude trees. What is important, particularly important in reforestation and in trees generally, is to understand what is a shade-demanding tree and what is a light-demanding tree, because this doesn't seem to have been taken into account in forestry, in modern forestry. This is a photograph taken on my property in Australia shortly after I cleared some land around these 2 trees. This area under here was covered with a very dense undergrowth, lantana it's called, which goes wild in Australia. And so these 2 trees, which are these 2 trees here, grew up with the bottom part of their trunks protected from light. About 4 weeks or 2 weeks or so, somewhere in that sort of period, I noticed that one of the trees was growing some branches on the lower part of its trunk, and the other one was not. And I'd been looking at this because I had also been studying this with been involved with Viktor Schauberger's concepts for quite some time. Okay, now this just to show you what happens what can happen under river regulations as they're carried out today. The outline here, this green outline and blue outline, is the original form of the Rhine, how it chose to flow in that particular situation. It may have begun to flood because, of course, the forest would have been cut down, although Germany hasn't cut down nearly as much forest as other people have. And maybe it was some way it became inconvenient, or perhaps it was not navigable, and they wanted to use it as a waterway for transport. At any rate, this was installed instead, which is a canal of constant width and constant profile. And suddenly what had been a live thing became constrained in this terrible straitjacket, which didn't allow it to move, and the energies gradually die in it. And so this river has constantly to be dredged. It's not a river anymore, it's a sewer, finally, because instead of the sparkling water that the Rhine used to have, you know, the Rheingold was what people spoke of, and that was the Rheingold was because rocks rubbed together of a certain composition on the bottom due to the coldness of the water and the natural flow, producing a glow which is known as triboluminescence, a goldish glow. So people used to see at night glowing along the bottom of the Rhine, and that was the Rheingold. Well, there's no way you can see that today because it's a grey-green, muddy, slimy, inert brew, and that has all really been caused by the shoving it into a canal of constant width. I think one last thing needs to be said about water, and this is only very, very brief, and that is that probably the best containers for putting water in if you want to store it are either egg or amphora shapes, because the egg, again, is a form specifically chosen by nature for the maintenance or continence of life. She didn't choose cubes, didn't choose spheres, didn't choose any rectangular shapes, and water contained in this terracotta vessel would maintain its vitality for a very long time. Firstly, it's cut out from light, so that no light gets to water. The light is, and sun and heat are the great dangers for water. And if the porosity of the material is correct, then for each 600th part of the contents that evaporates, the contents will be cooled by 1 degree centigrade. So that if this started out at 20 degrees centigrade, it very quickly would come down to a very cool temperature. And not only that, the water inside it would, because of cooling on the outside, it would descend in a spiral on the outside, moving the central water up, and so there would be continuous circulation. And in such a shape as this, there are no dead corners, no stagnant corners, which there are in cylindrical containers and so on, where there's no movement. And of course, once there's stagnation, then bacteria and all other sorts of things can develop. Now, of course, apart from water, which is fundamental to all life, without the forest, there's also no life for us, because the forest controls the climate. It controls the distribution of water vapor in the air. It also enhances fertility because it keeps the groundwater table up. There's many things that the forest does. It tempers everything for us. So without forests, in fact, we have no future, which is why I put this up. And this is one of the things that I think has to be pointed out, that while it is very important that all sorts of devices should be designed and produced to create free energy or as cheap energy and as environmentally sustainable energy as possible, the bottom line is there has to be some greenery out there, because if there's no greenery out there, there's no oxygen and there's no life and there's no rainfall, because everywhere we've seen that the forest has disappeared, then the drought has moved in. So it is a fundamental importance for us that we should plant more trees as fast as possible, and in fact one almost might say that all the unemployed people who are unemployed at the moment, of which there are vast numbers in most of the so-called civilized countries, they could quite easily put their hand to reforestation if it was done organized properly. But what we really need to find out too is what value do trees have for us? This is an evaluation of a 100-year-old tree by Waltera Schauberger and what it actually has done during its 100 years of life. And during this period, it has photochemically converted 9,100 kilograms of carbon dioxide and 3,000 liters of water. And it stored about 23 million kilogram calories which are equivalent to 3,500 kilograms of pit coal, and it is made available for the respiration of man and beast 6,600 kilograms of oxygen, so that in its 100 years life this tree has produced 6.6 tons of oxygen. In addition, it has evaporated into the atmosphere at least 2,500 tons of water, and has supplied a member of the consumer